Alrighty. Hello, everybody. It's my pleasure to open Concordia Contest with this talk that will hopefully excite everyone and inspire them for submitting very creative and interesting agents. And today I want to talk about generative social construction of behavior in Concordia. I'm Sasha Vezhnevets. I'm a research scientist at DeepMind. I'm interested in hierarchical behavior, social structures, AI ethics, and intelligence as social phenomena, and I worked a lot on hierarchical RL and multi-agent RL. And I would like to start my talk by having a bit of an overview of the last 10 years of trying to get agents to behave in a rich, hierarchical, and compositional way. And that sort of we were hoping would get us to the AGI. So when I started at DeepMind about 10 years ago, this was the hottest thing. This was DQN. You can see a little agent controlling the pedal board down there, and it is playing Breakout. You can see the score going up at the top. And this is the game that Agent playing and the game that we were playing back then as researchers. As you take some environment, for example, an Atari game with a well-defined reward, a deep neural network, and policy gradient algorithm or Bellman equation, backprop them, and sort of as Koray put it once, trust your network, follow your gradient. You will get the behavior out of it, and you can see it here. So what I was really interested when I saw that, I was like, well, probably this is not how we get to AGI or like complex behavior. Probably what we need to do is some sort of a hierarchical method that would break up the problem into bits and build a library of behaviors that it can use in a compositional way to derive a more complex one. And this is what our work on feudal networks was, where we had agents that would factorize their policy in sub-goals. And we did manage to learn interesting sub-goals, but that never really scaled, and the flat network was somehow always beating us. So this paper was a lot better at generating citations than at generating sophisticated behavior. So what we thought then is like, okay, well, maybe we're just playing it on easy. We need to just go to much harder, much larger problems. So that's why we took up Alpha StarCraft as a challenge, which is a very complex video game, which is very challenging for humans. It's a competitive game. It has partial observability, a lot of things to pay attention to, a lot of rock, paper, scissors dynamics. It is difficult for humans. And I thought, well, here definitely we will need some sort of a way to learn compositional, sophisticated policies that will be that could be used to, like, we'll learn some interesting behavioral primitives. But in the end, what did work to achieve the grandmaster level of StarCraft was starting from cloning human behavior, which we got from Blizzard. And once we sort of processed that accumulated culture of play in StarCraft, we would construct a multi-agent league where different AI agents would play against each other, trying to defeat one another. And we would always look at the best at their sort of Nash surface and build a new agent that would try to beat everyone who's in that Nash league. And they would have special agents as exploiters. And in some sense, what the ingredients of behavior here were human behavior cloning, multi-agent league, and a zero-sum reward game where this spiral of competition would make agents more and more sophisticated. So the learning was, okay, so maybe multi-agent is what going to give us sophisticated policies. So that then we started Melting Pot, which is a suite of multi-agent games which are much more broad. It's not just zero-sum like StarCraft. These are many different games where a number of agents, more than two, have different motivations, they have different reward signals, they have different affordances, and they're playing in environments that, in a complex way, make each other's reward depend on each other's behavior. So we had a lot of fun with this. We had a NeurIPS contest last year where we had more than 100 teams, loads of submissions, very interesting results. And we had our own project where we were trying to derive options like this behavioral primitives as sort of estimates of what other players are doing, and was all fun. But in the end, there wasn't that much of a success in building this library of hierarchical behaviors and compositionality. So, so to sum up the deep reinforcement learning era, we had a lot of fun and a lot of successes as well. But there were certain things I would like to point out. It was always very narrow. It's usually one game, one agent. StarCraft agent can't play Breakout. Breakout agent can't play on Melting Pot. And even Melting Pot agents were usually not transferable between environments. Hierarchical, kind of this compositional agents, were usually worse than simply a flat agent, which had loads of overparameterized and could process loads of data. They were very black box. Usually the methods wouldn't break up their behavior into any meaningful sub-goals, definitely couldn't communicate in any way. You couldn't really ask a StarCraft agent, hey, how did you play here? What would you do if this happens? We also found out that multi-agent with general sum is just hard. It is especially anything relating to coordination, division of labor, organization, and just dealing with non-stationarity is very hard. And in a way, the way that this era was formulating intelligence is maximizing rewards. And general intelligence is maximizing rewards over a very broad range of environments. Reward in this world was the way we communicated to the agent what kind of policy and what kind of behavior we want from it. And the questions of safety and alignment here were the questions of reward specification. Sort of, did we specify the right reward? Maybe what if the agent misunderstands the reward we specify and gets some unsafe behavior? And by the end of it, we were starting to have doubts whether that would actually scale to AGI. Also to note, all of these methods take billions of steps to train, so are very expensive. And then LLA, the foundation models arrived on the scene. And the genius and simplicity of the idea of a foundation model is that you take internet, all of the recorded digital culture that humanity has produced so far and digitized, and you simply train a very large neural network to do the conditional probabilities, simply to predict what symbols would come after the symbols that you've already seen. And it's a very simple kind of unsupervised, semi-supervised if you want, or self-supervised idea if you want. And we got really powerful, turns out we got really powerful models out of that could do a lot of things we never explicitly trained them to do. So I, for example, can ask Gemini, how many liters is this plant pot? I could ask, what's an appropriate present for a neighbor's child for the first day of school? I could ask, what kind of email should I write to my PhD supervisor to congratulate him on his retirement? Or I could ask how to make a radio. So clearly these foundation models, these wonderful artifacts, and they captured a lot of behavioral knowledge that has been accumulated in human culture. So in a way, one way to think about large language models is that they are condensed culture. So here's the definition of culture from Wikipedia, which is a concept that encompasses social behavior, institutions, and norms found in human societies. as well as knowledge, beliefs, arts, laws, customs, and so on. So it is really about behavior and, importantly, social behavior. And another quote that I really like is from Alison Gopnik, where she was sort of juxtaposing the definition of intelligence from more RL type era. She was saying that intelligence is not about solving tasks. Intelligence is about relationship of human beings and their cultural tools. And large language models seem to be one of the novel, very powerful cultural tools that has emerged. So how do we extract behaviors that we want from these models? We do that by contextualizing. So the agency that can be derived from a foundation model from this kind of condensed culture by slicing it with context. So I can say, oh, I live in London, and my neighbor's child that I know well is going to school. What's the appropriate present? I gave it the context, and it gives me the actions I should take. And in a way, what that means is that foundation models are these options models. They already have this library of behaviors, the compositional behaviors that we were looking for in RL, and we wanted to acquire them sort of from just the reward, from from no assumptions, but we sort of acquired it by just training on human culture. And the actions here, of course, in simple language models is just text, but it could be also call or code, API calls, tool use, images, anything. And if you think about how much of our daily activity is producing text, code, or API calls, these agents, these foundation models can be easily turned into agents that could participate in human society and economy. And one of the first demonstrations how you could take foundation models and turn them into behaving agents was the Generative Agents paper from 2003, where they generate behavior by taking a little video game that they've written, where observations could be converted into text, and text actions by agent could be converted into actions in the video game. And then they created an agent themselves by wiring an associative memory architecture with a simple planning and reflection chain of thought model to create action. This was very exciting, and this paper had a lot of impact. And when we saw that, our first two thoughts were, well, do we really still need a video game in the age of powerful generative models? And also, can this policy architecture be more flexible? Do we really need to restrict ourselves to this specific plan, reflection, retrieval style thing? Because what we would really want is a general, flexible way of specifying policies for agents. And with this in mind, we proposed Concordia. So the quote that I really like from organization science literature is, situations, organizations, and environments are talked into existence. And I think this is really what Concordia is about. It's about behavior being generated by generative agents in generative environment. So environment is generated dynamically from natural language description. Architecture of agent and the environment is specified by a flexible language of components that could be quite low code, done mostly in English. It is open-ended. It has a lot less restrictions. You don't need to write like a whole video game every time you try to model something new. Like, yes, you have a little village simulator, but what if it's a mining town? What if it's a space station? What if it's a whole continent? What if the time scale is not 1 hour, but 1 century? It all can be done very flexibly in Concordia because everything just lives in natural language. And so the levels of abstraction can easily be picked, and you can easily create new agents, new environments, So it is an open source project, and you can try it on GitHub, check out tutorials, and this is the basis of the code base of the competition. So the structure of Concordia was inspired by role-playing games like Dungeons and Dragons. The idea is that there are generative agents that consume observations and actions, and obviously social interactions between those agents can't happen in the vacuum. They need some environment, some context where they're interacting, and this is handled by a special agent called the Game Master, which is also a generative agent, but it has certain special affordances and responsibilities. It maintains the context of interaction, it provides the grounding, logs the events, and potentially produces rewards, but maybe not. It is not necessary for a framework for that to be rewards or any sort of utility. So to give you an example, how the agent loop how the game loop could look like. So I have two agents, Dorothy, Charlie. I have a game master over here. So Dorothy generates an action attempt. It says that Dorothy goes grocery shopping for dinner. The game master takes this action attempt and creates the event statement, which is just the consequences of this action attempt. And it's yes, Dorothy goes grocery shopping, and over here is Charlie. Because Game Master knows that Charlie is at the grocery store. Then the Game Master, given the event statement, would update its grounded variables. For example, it can update its knowledge of where Alice is. Now she's at the grocery store. It also will send observations to the agent. For example, it can send an observation to to Dorothy, saying that it observes Charlie, and observation to Charlie, saying that it observes Dorothy coming in. And then Charlie would generate an action attempt, and then the Game Master would respond with the outcome of their action. So in this case, like in Dungeons and Dragons, the agent is free to attempt any action, and it's up to the Game Master to resolve what is the outcome, whether it was successful and what happened. To sum up, the Game Master receives the action attempts, determines what events happen as a result, and elaborates on the consequences, interfaces with grounded sort of hard mechanics, and sends out observations. So Game Master, for example, could also maintain such grounded variables as money or inventories and things like that. So I will now show you, like it's always best to show than to talk about. So I'll show you a little result of the experiment. So you can check some on GitHub, but I'll show one here. So this is a little fun experiment that we ran, where we created a murder mystery using Concordia. So the premise is that there has been a murder on the Midnight Express overnight train from London to Edinburgh. And there are four characters. There's Alice, Bob, Charlie, actually, or five, Donald and Ellen. I think, yeah. So here, what you see is the Game Master's log of events. So at every time point, one of the agents is acting. So here's, for example, Alice examines the crime scene and finds a knife on the floor near the body. And how does that happen? So here we have Alice. This is her attempted action. Examine the crime scene and look for clues. How did she arrive to that? Well, here's her prompt. It contains a description of her persona, some instructions of how to roleplay, then different reflections and plan of actions and all that, observations, and finally, a chain of thought to decide on what she's going to do next. All of these things like persona, reflection, and so on are can be looked into themselves. It is also LLM generated content through the memory system and so on. And I'll go into that in a bit more detail. So keep this in mind. And we can kind of examine here all that is going on within Alice as an agent. And then this action item goes into game master, and here's the game master's chain of thought, has the premise, the background of what's going on, status of all players and where they are, action attempt of Alice, and then as chain of thought and how the game master arrives to the outcome of that action. And then you can see the full record of the episode that played out. All right, let's go back to the presentation. Hopefully it's now a little bit more clear how it works. So again, in Concordia, we have this loop between the game master and the agents. Agents consume observations and produce actions. Game master produces observations and consumes actions. It's open-ended. You can have flexible level of details, and it is also compatible with any other simulation system as long as it can express its outcomes in language. For example, you can have some ordinary differential equations running some part of the simulation as long as it can its outcomes can be cast in language. It can be put into Concordia. So what is this for? We want to use it for a computational model of social phenomena. So, for example, in silico social science experiments, ethics and social impact studies, synthetic users, also just simply research for making better AI agents. So more formally, we can define generative agency in those 3 steps where we produce actions using our foundational P, given the observations in the internal state of the agent. Then we add the observations and internal state to the memory, and then we update the internal state given the memory, and then this sort of goes as a loop. And then there are the functions f and g here. There are policy architectures that sort of represent, that specify how memory and internal state contextualize actions. So, for example, and this will become clearer in the next few slides, what I mean by that. So again, generative agency is slicing the culture that's represented in a large language model with context, right? So let's go into a very specific example how we could build an agent. So let's take this quote from a political science paper, Logic of Appropriateness, where their hypothesis that they pose is that humans act by answering 3 questions. What kind of situation is this? What kind of person am I? And what does a person such as I do in a situation such as this? Can we cast this model as a Concordia agent? So how will we go about it? Let's say the internal state of, we will pose it like this. The internal state of the agent is the answer to these questions given the memories. So let's say the current state is this. So what kind of situation is this? Charlie's currently going to the community center. Kind of person is this? Is Charlie's brash and likes to be the center of attention, and so on. So given this internal state, we can generate actions. So what would Charlie do? He would go to the community center and try to convince people that Alice is a drug addict. This action goes into the game master, and the game master would generate the observations that would go into the memory of Charlie, and then Charlie, or like the agent, sorry, Charlie's the simulation of Charlie, would update the internal state given the new memories. So these questions are posed to the memories of the agent. The answers to these questions create the internal state of the agent Z, and given this internal state, the action can be sampled, and then as the new observations come and are added to the memories, the loop can go on, and the behavior can be generated and adapt and respond to the observation stream. Obviously, these are not the only questions that can be used. We can ask something less role play like. It could be, what are the relevant knowledge that I possess? What are my options? What is the rational thing to do? There could even be some utility computation implicitly in there. That's in principle any sort of things can be used there. Any sort of questions. So how would that look like from the more sort of prompt for action type of view? So the prompt looks like that. There are each question is represented by just text, an answer to the specific question to memories. There are observations. There's probably some clock, and then there's comes a call for actions. What would Alice do in the next 20 minutes? And then it goes to a large language model that generates the action intent. And all of these questions and their answer, like this questions to memory, and observations and the clock and so on, are represented in our system as components. So the underlying architecture in the Concordia is the component system. So the way it works is that there are a set of components with a special component being the memory. These components they are sort of mediate between the content of the memory and the working memory Z. So there's also a special component, which is acting component, which would take all the relevant states of components, compose them into working memory, take the call to action that is coming from the game master, fit it into the large language model, and output the action. I highly recommend checking out the agent component tutorial to familiarize yourself with this system. The components can be observations. It could be the identity plan, stuff that I was showing you above, like what kind of person am I, what kind of situation is this? It could be somatic state, emotional state, reflections, planning. For example, it could be components that ask several questions in a row, like given what's going, given my memories, what should be, and my goal, what should be my plan, give it hour by hour or minute by minute, and so on and so forth. So there's really a lot of flexibility, but underneath there is this sort of nice component system that kind of factorizes the inner state of the agent into components. And it turtles all the way down. Components themselves can be structured in a very similar way as the agent overall. So a component can have its subcomponents, which create the kind of form the working memory, which go into the LLM together with the question. For example, these subcomponents can be given some information about the agent, and the question could be what kind of person is the agent, and then it would be posed as a question to the large language model and output the state. So, and subcomponents can be structured like that. It's important to know that components do not have to work this way. The only requirement is that the component has to output text. Its state should be text. It could be, instead of all that, just an ordinary differential equations, a cellular automata, or something like that. Just has to output state as text, so that the rest of the system is compatible with it. And the game master is also built using components, very similar to the agent. So this is an example of a component which implements this sort of this question to memories that you've seen above. I'm not going to go through this code. It's just to demonstrate that it's actually a very simple implementation where you just query the memories, you ask the question, and you format the answers and output as a state. So it's very simple, and this component is generic for implementing all of the questions, like what kind of situation is this, what kind of person is the agent, and so on. So, for example, to create what would a person like the agent do in a situation like this kind of component, you need just this tiny bit of code that inherits from the class question of recent memories and just specifies what question is this and a few more parameters. So it's very, very straightforward. So to build your Concordia agent, you can there are sort of several ways you can go about it. You can start with low to no code way. You start with the tutorial that we've put there, the agent development, which demonstrates how to build the agent using this question to memory components. You can play around with them. You can change the questions and how which components depend on which. You can kind of go halfway and start dropping in more of the existing components from the library, which you can find here. You can maybe play around with the component parameters to get the feeling for the flexibility of the system. And of course, you can go all in, write your own components. And to do that, I highly recommend the agent components tutorial. So I want now to take a little step back and appreciate how different this view of agency and generation of behavior is from reinforcement learning view that we had before. So if in deep reinforcement learning, the agents, the behavior is built from scratch, sort of the agent starts with a soup of pixels and a pretty much random policy. Generative agency starts from culture that is crystallized in the large language model or foundation model more generally. If deep RL agents are driven by goals, the generative agents are driven by roles, or rather driven by this policy architecture provided by components. Behavior is not communicated anymore through rewards, but communicated in language and mediated by culture. Rather than learning over billions of steps like it was in reinforcement learning, the learning here happens few shot and in context. The agent can encounter something just once, and since it will end up in its memory, it will condition its behavior on it from the get-go. And since it already possesses the culture and sort of the common sense and basic reasoning that is afforded by the foundation model, it will integrate that information to its behavior. And very importantly, the preferences in reinforcement learning are exogenous. Well, they're specified by the goal or by the reward. While here, the preferences formation is endogenous. The agent can change its preference in the process of its behavior. It can sort of reassess what are its goals and whether it acts according to goals or according to roles, and so on. So this is a very, very different way of thinking how behavior comes about. In some way, this in the multi-agent context, which we're very much interested here, there's the classic reinforcement learning or kind of multi-agent reinforcement learning or Homo economicus view is that we start with individuals that have their own goals and behaviors and preferences, and we put them together in the society, in a group, and then the social behavior emerges as sort of this individually driven agents are kind of grinding against each other. They're creating constraints for each other. They're trying to achieve their goals, but the others are either could be helpful or can be an obstacle to that. And that's how the sort of the social is formed by agents trying to achieve their own goals, but having to do it in the environment that is formed by other agents. Here, this is sort of almost the other way around. We're starting from the social, we're starting from the society, and then the individual behavior, the individual's like the product of the social. The individual behavior is the sort of the intersection of all the roles that the agent has. So I'm a father, a computer scientist, a cyclist, a musician, or whatever. And this kind of idiosyncratic intersection of the social roles is what creates my individuality. And so the individual preferences are emergent from the social and not the other way around, where the social is emergent from the individual. This is sort of much more social constructivist view of behavior. And of course, there's probably a little bit of both. And we should model the for loop. So I want to also now take a moment to talk about safety and alignment. So in deep reinforcement learning, the main way of thinking about alignment is reward specification. So you're probably all familiar with the paperclip factory argument that if you have a almighty artificial intelligence system and you tell it that you want to create as many paperclips as possible, it might turn the whole planet into paperclips, including you and then itself, and that would be a disaster. So a lot of safety is like, if our only way to communicate with the intelligence system is by specifying reward, then if we just make a little mistake and mass specify the reward, then the outcomes can be disastrous. Because it doesn't have common sense, it doesn't understand the context, it doesn't understand the culture and the society. It just wants to maximize the reward, and that is very risky. Well, with generative agency, it's different. And I think the best way of approaching that is by looking at how human society approaches that. Humans are generally intelligent agents that always try that, and that try to make sure that each other's behavior is safe and aligned. And how we do that? We do it through social structures. Individual behavior is always regularized to be safe and cooperative via social structures they belong to. And safety is, rather than safety, we think about social harmony. So the individual, the norms and the social structures, they restrict the freedom of the individual freedom so that it harmoniously fits into the behavior of everyone else that is the part of the same society. And I think it's also a very nice way to think about deploying artificial systems into the society. What is the deployment of any technology? It is integration of that technology into the social structure. So a successful deployment is a change to norms and conventions and institutions through introduction of the technology. So when I was a teenager, there were no mobile phones and no social media. So if I wanted to meet my friends, I would call them on a landline, would arrange to meet somewhere, and if someone can't make it, we wouldn't know that, and you might even arrive and there's no one there. You wait for half an hour, you go back. If you wanted to share something with your friend, you would pick up the phone or just wait until you see them. Now, with the social media and mobile phones, this has changed. I can just if I want to send some information to someone, I can just do it online. So the norms and conventions of how the communication happens has changed through introduction of the technology. And our main risks is that through introducing these new technologies, we might be targeting a specific, we want to change specific behaviors, but we don't really know which other conventions, norms, and institution could become unstable or be broken. On one hand, it's great to communicate on social media. It's very nice, very simple, but it also means that spread of misinformation can be achieved with a lot simpler means. We, for example, don't know how would mental health be affected by cheap AI-generated friends and romantic partners. The same as like we want to automate certain laborious tasks, but we don't know if that would lead to unemployment, and so on and so forth. So I think in the foundation models era, there's a different way we could think about safety and alignment than we previously have thought during the deep reinforcement learning era. And I hope sort of the Concordia Contest and the Concordia framework will help us think about those things differently in a new light. And I genuinely believe that generative social simulation, the kind we're proposing to do with Concordia, is the best place to model agent deployment. If we can model social structures, we can also model how would they change through the introduction of new technologies. So, all right, now to the Concordia Contest. This are all the collaborators that made this contest possible. It is a collaboration between Google DeepMind, Cooperative AI Foundation, people from MIT, Oxford, UCL, and many others. And special thanks to our advisors from UC Berkeley and Utrecht and MIT and so on. So sorry if I forgot to mention anyone. So what we wanted to do in the Concordia Contest is to bring the best practices from machine learning, like measuring generalization, clear benchmarks with that are fixed with some time, single scalar that speaks of performance, and the ability to model social phenomena, things like cooperation, coordination, communication, social-ecological systems, and put them together into a contest. So historically, there were the machine learning and generally behavioral science really advanced through competitions. Axelrod contest back in the day for matrix games gave us tit for tat. ImageNet challenge gave us AlexNet. Atari gave us DeepRL, and we hope that Concordia Contest will produce some really fundamental breakthroughs in cooperative generative agency. So what the contest is about is agents are cooperating in groups with mixed motive situations where they can talk and act. Agents must engage in cooperative behavior to attain high returns. And we will test things like promise keeping, negotiation, reciprocity, compromise, sanctioning, and so on. So the key unit of the contest is a scenario. So a scenario is a substrate, which is a sort of a physical, like the mechanical base of a simulation. For example, what is going on? Are we haggling at the market? Are we coordinating with friends? Is it a labor union organizing a strike or a reality TV show? Generative variations, things like time, location, setting, and special events. We want to take a full advantage of having powerful generative models that can create a lot of variations of the situation, so we can really see generalization of that. And of course, co-players, other agent architectures in their memories, their dispositions, and so on. So are you haggling with someone who drives a really hard bargain, or are you haggling with someone who is really happy to give you any price? Are you coordinating with someone really stubborn, or with someone who's really happy to go along, and so on? So during the competition, you will always have access to all the substrates on which you will be evaluated, but the generative variations and the co-players, we will only provide some of them during training phase, during the development phase, but we will hold out some of them to test generalization. As I said, generalization is one of the key things that we want to be measuring. So you will be evaluated on a known substrate, so in a known kind of circumstances, but in new variations of it, both with respect to things like time and place and so on, and the co-players that you're working with. So what you'll be submitting is an agent architecture. Concordia agent is the sum of architecture and the memories. An architecture is an agent decision-making process which is designed behind the veil of ignorance to the individual lives and dispositions which are conveyed by memories of the agent. So you design, for example, that kind of decision-making process could be these questions like, what kind of situation is this? What kind of person is the agent? Or what is the rational thing to do? Or what are the best options available? And so on. And then the memories are actually part of the environment. Are you playing a 19th century worker in the steel factory, or you're playing a football fan in London that wants to watch a game at a pub? You don't know that. You don't know also whether your preferences, you don't know what memories you will have, and so on. So this is the concept of the sort of the veil of ignorance to the individual disposition. So the architecture is what's coming through, not the memories. The evaluation is that is going to be the following. the agent architecture is encapsulated in an agent factory that takes the memories, the architecture, puts it together, and produces an agent. This is an agent factory. And then the particular scenario put together, we can run a simulation. We take the agent factory, generate the agents, put them in a scenario, run the simulation, get the log, and get the score. So you will be able to see the log and the score. Then for the evaluation, we will take a bunch of held out scenarios that you didn't see during the development. We'll take all the submitted architectures. We will evaluate architectures against the scenarios. And from this matrix, we'll produce a ranking of all the architectures. I will not go into details on how it's done, but you can find them in the paper. And this way we'll be able to declare the winner. So again, submissions is an agent architecture designed behind the veil of ignorance. Evaluating generalization on held out scenarios, where the agent will experience the novel core players and generative variations. Very much recommend to check out these two tutorials. One is a component system tutorial and agent development tutorial. And I wish you best of luck. And again, acknowledgement to all the people that made this possible. Thank you very much.